a few A2 exam style questions. These questions are spontaneous, extempore, so please bear with me. I'll be using my imagination to construct a few questions that I'll be resolving herein. So the first question I have in mind is a typical circuit with the ammeter and a resistor and a battery. A switch. The switch should have been here, but I apologize. And a capacitor, just a single capacitor of, let's just say, 10 microfarads. And let's choose the resistor to be 2 kilo ohms. And I'll give this a 20 volt battery, right? So my question to you is, find me the current in the circuit immediately after the switch is closed. So after I close the switch, I want you to find me the current. So how will we find the current? Okay, so we've got capacitance, which is 10 microfarads, resistance, which is 2 kilo ohms, and voltage, which is 20 volts. So I want you to find me the current. So we know that Q equals IT and Q equals CV. So we've got we have the C, the V, and we don't have this. So what so we need to find this, but we've got this and this, and what about this? Because this is supposed to be RC, so RC, C, what's happening here? Okay, so what we could do is we could use the ohmic relationship, and we can multiply 20 volts with, and we'll get 0.01 amps or 10 milliamps. So that'll be the answer, 10 milliamps. Okay, so in the same circuit over there, I then want you to find this final charge. So I was able to find the current. Now I want you to find the charge. The charge would be Q equals IT equals CV. So the charge, so I found this, and I have this. So I need to find Q equals CV. So the charge, this equation wouldn't apply because there's a we don't have time right now. So Q equals CV, and so the C is 10 microfarads times 20 volts. The charge would be 10 over always put the units. That's why I'm putting the units, because if you don't put the units, you won't get the marks. So that'll be 2 over 10,000, 1 over 5,000, so 1 over 5,000 coulombs. So that's what's that's a 2 raised to the power coulombs. So that's your answer. So now in this circuit, we had this, and this, and we were able to find the current, and by using the CV, we were able to find the charge. Now I want you to find the time constant. The time constant is very simple. That'll be capacitance, which is 10 microfarads. So that'll be 2 over 100, 0.02 seconds. We can't write seconds because it's less than 1 second, so we'll have to write sec. We can't write second either because it's not a whole second. So I hope you understand where I'm coming from. It's the same as mole, where you write, where if it's less than 1 mole, you write mole. If it's 1 mole, you write mole, and if it's more than 1 mole, you write moles. So this is how it goes. This is decimalized version of the unit. Right, so... Okay, so now I'd like to spice it up a little bit, and if I said that the time taken for one wave cycle of the charge, one wave cycle was 0.04 seconds, and the time constant was 0.2 seconds, and the voltage and the charge and the capacitance and the resistance was as above, which is 20 volts, and then it's 2 10 to the minus 4 coulombs. Capacitance is 10 microfarads. Resistance is 2 kilo ohms. Can you find me? Can you calculate the total potential capacity of the charger, of the capacitor, sorry. Well, charger is a capacitor, but you know. Can you? Yes, you can. The answer would be through voltage able to be pushed into a capacitor equals voltage supplied, and then exponent 1 minus T over tau. What's tau? Tau is the RC. There's the time cycle. So I'll be using this. So I'll simplify this equation. So I need to find this. So what I'll do is minus 2. Yep, 2. So that'll be minus 1. So that'll be the answer. So 7.4, and then the delta voltage, so would be 12.6. It would not always show the amount shown here. It would be a little bit less in real conditions because of eddy currents, material limitations, discharge potential, and so that's the answer to the first question. The capacity for it would be at 0.04 seconds would be 7.4, so 20 minus 7.4. Thank you very much, and I'll get to the next question. Okay, so I've got a question for you whereby I want you to define capacitance. So what is capacitance? What's capacitance? What is capacitance? We know C equals Q over V. We also know T over V. We also know T over R. We know this is right. This is how it is. But what is the concept of capacitance? A lot of books, they define capacitance as the ratio of charge to the potential difference. Ratio of charge to the potential difference between two plates of a capacitor. or a body and an earth. So this, I don't agree with this definition of capacitance because it really doesn't explain the nature of the phenomenon. The nature of the phenomenon, what is it? What's the nature of the phenomenon? Capacitance is the ability, the tensor limit of a charge storage body, be it a capacitor of any kind, to store charge against the work done by the circuit on the charge. So what happens is the capacitor is taking toll, is struggling against the work done on the charge by the circuit, because the circuit wants to drive the charge. It doesn't want it to stop somewhere, but the capacitor is working against the work done by the circuit on the charge to store that charge in its and store it for future use. However, this is not perfect. This is far from perfect, and capacitors have a tendency to leak over time. Capacitors will leak charge leaking, charge depletion. So charge leakage or depletion is the same as magnetic heating or eddy currents or internal resistance. So that's not in question right now, but the actual phenomenological definition is the tensor limit of a charge storage body to store charge against the work done by the circuit on the charge and store it for future use. So that's my understanding of capacitance. Now, my question to you is, for example, if we had a battery and its corresponding switch, yeah, voltmeter. Voltmeter is always in parallel. And what else can I put in? Yeah, let's put in a capacitor. So if I had a capacitor of 10 microfarads, again, I'm sorry I'm using the same figure, 10 microfarads. I could have used nanofarads, picofarads, but let me just stick to 10 microfarads for calculational efficacy. It's fully charged with a 20 volts. So hang on. So and this time I want you to calculate the following. And let me aim this as 2 kilo ohms. This doesn't matter right now. Let's not. This is variable voltage. This is the voltage of a series. It's a SAQs. So voltage will break, which is why we've got a voltmeter here to check the EMF. This is for EMF calculation, internal resistance. Let's not talk about this right now. Resistance would be and then so I want you to so let's just keep it as a template. So let's keep it as a template. I want you to, number one, sorry, I'm thinking as I'm going along. I want you to calculate the charge stored by the capacitor. So the charge would be, it would be Q equals CV, and we've got 10 microfarads times 20 volts. That would be Coulomb, because it's coulombic in nature, electrostatic attraction and repulsion. And then we calculate the energy delivered. So the second part would be energy delivered. Energy is work done, and that's QV. So I would do, I should have done, okay, so first let's just do QV. That'll be 10 microfarads times 20 volts. QV would be times 20 volts. That would be 4 millijoules. Now, according to the theorem, it should be half QV, so that would be 2 millijoules average RMS. So, and then the energy, and then we can do energy stored. So that was energy delivered. So how much is the potential energy? So that's the potential of deliverance. But this one would be potential of storage. Potential of storage. So the potential of storage would be that should be 2 millijoules, as I said earlier. 2 millijoules. Q times V, 2 millijoules. And now I want you to calculate the time constant. Time constant would be 2 kilo ohms times the capacity 10 microfarads. That should be 20 milliseconds. So yeah, that's pretty much it. So I gave you a circuit in the beginning. In the beginning there was a circuit with 20 volts battery DC, 10 microfarads capacitor, 2 kilo ohms resistor. So with all of these, I asked you to labor for me and calculate the charge. Then I asked you to give me the potential energy, total potential energy available in that capacitor. And then I wanted you to calculate the possible storage capacity. And then I wanted you to calculate the time constant. So I made you calculate quite a few things in a very short space of time. Okay, so now I want you to define farad for me. So farad is the System International unit of capacitance, and 1 farad is said to have been stored when 1 coulomb of charge has been deposited into the capacitor across 1 volt of potential difference. So that's the whole jargon-based definition of farad. And if it comes as a question in A2 exam paper, this is what you have to write. Farad is the SI unit of capacitance. And 1 farad is said to have been stored, or you could just say 1 farad is stored. You could just 1 farad is stored when 1 coulomb of charge has been deposited into the capacitor across 1 volt of 1 volt of potential difference. I'm going to ramp it up a little bit, take it up a notch, and induce a bipartite circuit. So I'm going to give you a circuit with 2 questions, but it'll be slightly technical. So this question is to do with a capacitor. So I'm just thinking with a resistor. Let me put a resistor. Let's just say 36 to mix it up a little bit. 36 kilo ohms. And I'll give this 10 volts for simplicity. And then let's mix and match a little bit. What else? Yeah, these two are going to the take them to the CRO, and what should I give this? So I'll give it 60 kilo ohms, I think. Yeah, that's what I'll do. Okay, so we've got a basic capacitance bipartisan circuit with CRO interference input. I want you to please ignore Hall effect. Ignore Hall effect. Ignore impedance, reactance, resonance. Ignore these. Okay, just focus on 60 kilo ohms CO, 200 microfarads, 10 volts, and 36 kilo ohms. I want you to, number one, give me, pause the video if you will, if you must, and give me, show me the time constant. Time constant. Show me the time constant is 6 seconds. Show it to me. And so this is what you could pause the video here and then show me, and then I'll show you the working. Now, I asked you to show me the time constant for charging to be 6 seconds. So T charging equals 6 seconds. Prove it. So we know T equals RC. So I would use 36 kilo ohms times 200 microfarads. Cancel. 36 over 5. Roundabout. Hmm. 6 divided by 5. 7.2. Roundabout 6. Because it's never perfect in real life. It's not perfect. You always get a second or two more or less, because this delay could be because of charging, device heating, mechanical resistance, electrical resistance, and whatnot. Next, I want you to show me the time constant for discharge of a capacitor, and I want you to, without proof, show me what the discharge of the capacitor would look like. So we all know it's this, and the resistance I'll be using is 60 kilo ohms times the same coulombs. So that'll be, yeah, that'll be synchrony, and I'll cancel 4 zeros out here, 2 zeros here, and that'll be 12 seconds. Yeah, it should be 12 seconds. So discharging is this is because this is due to discharging being a smoother process with negligible resistance. So this is why this comes out to be 12 rather than 14 something. And then I want you to look at the question and see that you were intimidated by the complexity of the question, and you were thinking about Hall effect, impedance, reactance, resonance. You don't have to. Just focus on this for the discharge, and that for charging, discharging, because here it's now right next to the battery. So the capacitor the resistor, we had two resistors, one CRO for wave function, and then one capacitor, 1 voltmeter, 1 voltage supplier. It was a DC. That's a DC. And DC volt supplier, and then resistance 1, resistance 2. Now for charging, this resistance would be used because this is closest to the battery, and this becomes the first impediment in the way of the capacitor to store charge. In terms of discharging, this one, the furthest away, the distal resistor. So proximal resistor, distal resistor. This distal resistor will be used because it's farthest away, and discharging would take place through this one because that's at the end of the circuit and this is at the beginning of the circuit. I hope this clarifies it, and I'll be taking you through some more questions. Bear with me, please. Okay, so I've got a question for you. So I've got a capacitor, and the capacitor's value is 200 microfarads, and the potential difference across the battery is 30 volts. Can you calculate the charge for me, please? Charge would be Q to CV, 30 volts times 200. Sorry, I'm using the same numbers over and over again for simplicity purposes to reduce the need for calculator. 6 over 1,000, so that'll be 0.006 millicoulombs, and that'll be 6 millicoulombs. So I took this and this, multiplied it, and I got the 6 millicoulomb. If I wanted to ask you to calculate the energy, the potential energy, that would you do half CV squared? Yes, because we don't have. We could do we could do QE, but CV squared is a bit of a fun as well. It's good. So although the other one was easier. So 0.9 joules. Okay, so 6 millicoulombs and 0.09 joules. Okay, so now if I had to mix and match, I would say I add 100 microfarad capacitor here. So how would it impact the charge, and how would it impact the sorry, I think in order to make it simple, I would say if I connected 100 microfarads in parallel to the 200 microfarads in the circuit, how would it impact the charge, and how would it impact the energy? So the total capacitance would be C1 plus C2, 300 microfarads. Now I want you to do the calculation with 300 microfarads. So you've got 300 microfarads, so you'll have to multiply 30 volts by 300 microfarads and get what? And then multiply 300 microfarads times 900 divided by 2. So then what would you get? So I'll do that for you and prove the impact of it. So now in the circuit we have the C is 300 microfarads. We have the voltage is 30 volts. Now we want you to find out Q equals CV, and that would be so that would be 9. So first it was 6 millicoulombs, and now it's 9 millicoulombs. So the charge has gone up with the capacitance. Why? Because Q and C are directly proportional. So if the capacitance goes up, the charge will go up as well. That's for that's for capacitors connected in parallel. It couldn't be said for the same. Can't be said for capacitors in series. But right now we're examining capacitors in parallel. So if I added 100 microfarad in parallel to a 200, it would lead to a total increment of 300. 300 when put into this formula for charge calculation would lead to the charge discovery of 9 millicoulombs, which is more than 6 millicoulombs, because charge. So we can now verify that charge and capacitance are proportional, and an increment in one leads to an increment in the other. So now what we need to find out is the energy. So has the energy increased as well? It should. It definitely should. Capacitance. Okay. Squared. 27 divided by 200. Joules. That would be, I think, 0.54 or 0.135. Yeah, 0.135. Let me double check. Yeah, 0.135 joules. So you can see that it was 0.09, not 0.09 joules, and now it's 0.135. So there's been, in conclusion, there's been a 1.5 times increment in charge storage, and a 1.5 times increment in the energy as well. So that's for parallel plate capacitors. So that's parallel capacitors in parallel. Now, what would happen if we added 200 microfarad in series? So if we added it in series, so that would be 1 over 100 plus 1 over 200. Sorry, 2 plus 1. 200 over 3 microfarads. That would be 60 something, 67 microfarads. So without having to do calculations of charge and energy, we could see that because the total capacitance has gone down, the charge and the energy are bound to go down as well. So that's why capacitors are added in parallel and not in series, and resistors are added in series and not in parallel. Thank you. That concludes our session on A2 exam questions for capacitance and capacitors, and I hope you learned something today, and I'll take it from here. And if you have any questions, please post them down below, and I'll try to try my best to answer them and resolve any mathematical conspicuities to the best of my ability, and I'll take it from here. Cheers. Take it. Bye now.